In this video, we are going to start our discussion of conditional probability. This topic is divided among two videos. So this first video will cover the first 5 topics, and then our next video will cover tree diagrams and Bayes' theorem. This is our overview slide, which we'll spend maybe a little over 5 minutes on, but not much more. And then we'll go over the first 5 topics in more detail and with more examples. Our first bullet is just kind of a quick introduction to the ideas of conditional probability. So when assessing the probability of an event, knowledge of a different second event might change our probability assessment of the original first event. And then something I'll explain in the main part of our video a little more closely, that's because the event space is made smaller. An example of a conditional probability, I might estimate the probability of rain next month, but I might update my estimate if I know some probability of storm clouds next month. So my original event is rain, and I'm trying to estimate the probability of rain, but I have the second event, storm clouds, and the probability of storm clouds, once I know the probability of storm clouds next month, I might update my probability of my original event, the event of rain. Because conditional probabilities now involve more than a single event and probabilities for multiple events, we need to talk about marginal and joint probabilities. So marginal probabilities are based on a single variable or single event without regard to other variables, whereas a joint probability is probability of outcomes for 2 or more variables. And we'll look at examples of tables showing marginal and joint probabilities and figure out how to read and interpret them. And then we get into our main topic, conditional probability of outcome A given condition B. So this is the formula here, and it's what probability of A, this vertical line is read given. So probability of A given B is equal to the probability that both A and B occur divided by the probability of A. And just a quick reminder, because I use this notation quite often, when I notate probability of A and B occurring, I often just separate probability of A, comma, B. So it's just a list of the things that must occur. It's not an or, it's an and. One other thing, this is the alternate form that I like to remember. So you can get this alternate form by taking this formula, multiplying both sides by probability of B. Then you get the probability of A and B is equal to the probability of B times the probability of A given B. And the reason why this is more memorable to me, this is the probability of A and B both occurring. So that's the probability first of B occurring, and that's what this multiplication is, that's the multiplication rule, and the probability of A occurring after we know that B has occurred. So 2 things have occurred. First B, and then probability of A given B. Remember, our estimate for probability of A changes once we know B has occurred. We can also look at this another different way, which is the probability of A occurring first, and then the probability of B given we know A has occurred. I like to give this as my first example for conditional probability, a bucket with 3 red balls and 3 blue balls. So here we have 3 red balls, 3 blue balls. 2 of the red balls have a number 1, and the other has a number 2. 2 of the blue balls have a number 2, and the other has a number 1. What's the probability the ball is 1 given that it is red? We can look at the picture and find the answer. 1, we're given the ball is red, so we're only concerned with these 3 balls. And this is what I mean by the sample space is made smaller. So now the number of outcomes that suit our condition, that it's red, narrows our sample space to 3 different outcomes. And now, what's the probability it is 1? Given it's red, that's these 2 out of 3. So the answer is 2 out of 3. But let's also get that 2 out of 3 by using this formula here. We're going to let A represent the color is equal to red, and B that the number is equal to 1. So the probability A and B, in other words, probability color is equal to red and number is equal to 1, is equal to, and we're going to use this side of the equation, probability it is red, and then probability it is number 1 given it is red. Okay, so we're following this part of the formula. I can now look up This part, probability, is red and number 1. So red and number 1, there are these two cases out of the total 6, and it's equal to the probability it is red. That's 1/2. And now we can figure out the probability the number is equal to 1 given the color is red by dividing the 2/6 by 1/2, and we get 2/3, which is exactly what we had noted before just by looking at the drawing. The interesting thing about this conditional probability is it is a generalization of the multiplication rule for independent events. Remember, if A and B are independent, that means even if you know A has occurred, it doesn't change your assessment of probability of B. Like one event occurring doesn't tell you anything about B. So if A and B represent events from different and independent processes, we had this multiplication rule. Probability of A and B occurring equals probability of A times probability of B. So let's compare that to our conditional probability rule. And in particular, we're going to look at probability of A and B is equal to probability of A times probability of B given A. So this is where we differ, right? Otherwise, the formulas look the same. Probability of A and B, probability of A. So remember, if they're independent, the probability of B given A, even if you know the outcome of that A has occurred, it doesn't change your assessment of probability of B. So probability of B given A simply becomes probability of B, and you have this general multiplication rule for independent events. We have this sum of conditional probabilities. So if we have disjoint outcomes, in other words, outcomes that cannot occur at the same time, A1, A2 up to AK for a variable or process, then if B is an event, we have probability that A1 occurs given B plus probability A2 occurs given B all the way up to probability AK given B equals 1. That assumes that A1, A2 up to AK, those are all the possible outcomes for this variable. And probability of A given B is equal to 1 minus probability A complement given B. Even though we're not going to talk about tree diagrams until our next video, I'm going to give you a little bit of an overview. We're going to use this bucket of balls, except for some reason I forgot these blue ones were blue and I labeled them as white. So we have red balls and pretend like these blue ones are white. So tree diagrams represent outcomes for a multi-stage process. So every time there's something that's happening, like here, you're drawing two balls. You're drawing a first ball and a second ball. So each stage represents a new branch of the tree. So we start off here, and the first stage is determining whether we drew a red or a white ball. In this case, there's an equal probability of choosing a red versus a white. So we're going to label the probability 1/2 for red, 1/2 for white. The next stage, we're going to determine what number was drawn. If we have followed the branch of the red ball, there are 2/3 probability of getting a 1 and a 1/3 probability of getting a 2. So our 1 has a 2/3 probability, our 2 has a 1/3 probability. If we had followed the white branch, then there is a 1/3 probability of getting a 1 and a 2/3 probability of getting a 2. So we have 1 has a probability of 1/3 and a 2 has a probability of 2/3. Now we can follow any branch. Let's say we want to know the probability of getting a red 2. So we follow the red branch and then the 2 branch. So the probability of a red 2 is going to be 1/2 times 1/3 or 1/6. Probability now of getting a white 1, we'd follow the white branch and the 1. It would be 1/2 times 1/3. And you can see the rest of this diagram. And then finally, we have Bayes' theorem that is in this form, given to us in this form. It's really just an extension of our conditional probability along with the sum of conditional probabilities formula here. And we'll go into that in our second video. So that concludes our overview. So now we'll go back and talk more about conditional probability and marginal and joint probabilities. In our overview, we talked about conditional probability comes when we're assessing the probability of an event, and we have knowledge of a different event that might change our probability assessment of the original event. And we talked a little bit about how the event space is made smaller when we were talking about the bucket of balls, and we made the event space smaller. In other words, we eliminated some of the possibilities. We eliminated the blue or the white balls and focused only on the red balls. And that's how it is that our probability assessments were different. We'll look at this with a few other examples. The other example I talked about for conditional probability was estimating the probability of rain next month. But it might be the case I would want to update my estimate if I know the probability of storm clouds next month. Another example your book gives you are car insurance companies. They will consider information about a person's driving history to assess the risk they will be responsible for an accident. So in this example, the event we're trying to predict is that a particular driver will be in an accident or responsible for an accident. The event that will change our probability assessment of this, so the additional information, is the driver's driving history. And so the event might be the number of accidents in the last year. So given the number of accidents last year, we might change our assessment of the probability that the driver will be in another accident in the future. And again, just to look at that example we had before in our overview, a bucket with 3 red balls and 3 blue balls, 3 red, 3 blue. 2 of the red balls have a number 1 on them, and the other has a number 2. 2 of the blue balls have a number 2 on them, and the other one has a number 1. So what's the probability we draw a ball with the number 1 on it? So we shake up this bucket of balls. What's the probability of drawing a number 1? Well, there are 3 ones out of 6 balls, so we have a probability of 1/2. Now we have this conditional probability because we're given extra information about one of the variables. We know now that the ball is red. So now all of a sudden our event space or our possibilities has gotten smaller. And so now what is the probability that the ball has a number 1 on it? Well, there are 2 possibilities out of 3, so 2/3. So the additional information has changed our event space. That is, the additional information has eliminated some of the possible outcomes, some of the possibilities. Because conditional probabilities talk about multiple events, we have our original event and then the event that might change our assessment of the original event. We have the idea of marginal and joint probabilities. In other words, now we have 2 variables. So marginal probabilities are based on a single variable without regard to other variables, whereas a joint probability is a probability of outcome for 2 or more variables. So let's do an example. Your book gives you this example and uses it extensively in this chapter, so we should become familiar with the ideas. So first, data scientists have been working to improve a classifier. So the classifier is a type of machine learning computer program. So there's this machine learning, we'll just say ML for machine learning. Data scientists have been working to improve a classifier for whether the photo is about fashion or not. And there's 1,822 photos that represent a test for our machine learning. So the idea is we have this program called a classifier that you can present it a photo, and we have this data set, a sample of 1,822 photos that we can test then our classifier to see if it can recognize whether a photo is about fashion or not. So you give it a photo. If it's a photo of a landscape, it's probably not about fashion. If it's a photo of someone dressed in some really either fancy or outrageous clothing, it's probably about fashion. If you have a group of people standing around talking in some nice clothes, whether or not it's about fashion, that's like a little bit harder to classify. But each photo gets 2 classifications. The first comes from our classifier, our machine learned, which gives either a predict fashion or predict not. So our computer algorithm, our machine learning system, our classifier, predicts that the photo is about fashion or predicts that it's not. And then the second classification has been done by a team of people, a team of, I guess, supposed fashion experts. And we're going to take their word to be the source of truth. So they'll tell us whether the photo is really about fashion or not. So truth versus our machine learning. First, let's talk about these numbers here. they are going to help us with our joint probabilities. And that's about probabilities for two or more variables. So these numbers talk about two or more variables. They are not our probabilities, but there are counts that we will use to calculate joint probabilities. So let's look at these counts. Why are they about two variables or more? In the columns are about the truth, what the experts say are about fashion and not. So if it's in this column, these counts belong to the photos that the experts said were about fashion. If it's in this column, these are the counts of photos that the experts said were not about fashion. When we look along the rows, then these counts, these two numbers, represent the photos that the machine learning predicted to be about fashion. And this row here is the counts, the photos, that the machine learning predicted not to be about fashion. So now, if I look at one of the numbers, let's look at 197, what that tells me is there's 197 photos. It's in the column that tells me the expert said it was about fashion, and the machine learning, I can look at the row it's in, the machine learning predicted it was about fashion. If I come over here, I'm in the column where the expert said these 22 photos were not about fashion. However, our machine learning, it's in the row that the machine learning said incorrectly that it was about fashion. This 122 then represents 112 photos that our experts said were about fashion, and our machine learning, because it's in this row, incorrectly predicted it was not about fashion. And then finally, we have these 1,491 photos that experts said were not about fashion. It's in the not column, but our machine learning did predict correctly also that it was not about fashion. And by the way, if you add up all these numbers, you should get a total of our 1,822 photos. We can use these counts that concern both variables to then get data for our marginal probabilities. In other words, we can get counts that concern only one variable. So for example, let's talk about the variable truth, what the experts say. If we want to know how many the experts said were about fashion, we simply add the column here. So when we add 197 to 112, we are going to get 309. When we want to know how many photos did the experts say were not about fashion, we're going to add the 22 to 1,491 to get 1,513 photos. And again, if you add these two, the 309 to the 1513, you should get our total number of photos. So in this way, we have counts, marginal counts, that later we can use to figure out our marginal probabilities about this one variable, what our experts said, the truth. We can also now get our marginal counts for our machine learning. This is about the variable that our computer program classifier had come up with. If we want to know how many photos in total that it predicted as fashion, we would add up the row for predict fashion and get. So we have 197 plus 22. So what is that? That would be 9,219. As for which photos or how many photos it predicted were not about fashion, we'd add the 112 to 1491, and we'd get 1603. So this is our marginal count for our machine learning, and the total, the 219 plus 1603, should add up to our total 1,822. So again, we haven't calculated probabilities yet, but these are the numbers, the counts that will help us. Here are the counts that concern our two variables. Here are the counts that concern our one machine learning variable, and these are the counts that concern our one truth variable. The marginal probabilities are actually pretty easy to calculate, so let's go ahead and do that. So let's look at the truth, the one variable about whether or not the experts thought this were about fashion or not. We said 309 they thought were about fashion, so that's 17%. That's the marginal probability that this one variable went for fashion. And then the marginal probability for not, that would be the total of our 22 plus 1491, or the 1513 divided by our total number of photos, 1,822, that's 83%. Our marginal probabilities for machine learning, predict fashion, that was a total of 219 divided by our total number of photos is 12%. Predict not fashion, that was our 1,603 divided by our total 1,822, which is 88%. Our first question is, if a photo is actually about fashion, that is, truth is equal to fashion, what is the chance that the machine learning classifier correctly identified the photo as being about fashion? So first, this is an aside. This does not answer the question, okay? But the machine learning predicts fashion 219 times out of the 1,822. So 12% of the time, machine learning equals predict fashion is 12%. But now we have this additional information, right? So first, machine learning was predicting about fashion, but we have this additional information that the photo is actually fashion. So we're going to focus on these counts here. So the probability that the machine learning predicts fashion, given that truth is fashion that we're looking at this data, is 197 times out of a total of 309. Remember, now it's like that bucket of balls. We're ignoring all of this data and only looking over here. So that's equal to 63.8%. So it's gone up a lot. If we're actually looking at a fashion photo, it'll predict that it's a fashion photo much more frequently. Our next question, we sample a photo from the data set and learn the machine learning algorithm predicted this photo was not about fashion. What is the probability that it was incorrect and the photo is about fashion? Now we are looking at the data. We've had this additional information. The machine learning predicted it's not about fashion. So we're looking at this part of our data count. So if the machine learning says predict not, we are looking at the data in yellow, and then the probability that the truth is equal to fashion given machine learning equals predict not is equal to, well, if the truth is fashion, that's 112 out of, in this case, 1,603. So it's 6.98%. Now I can compute the marginal probability of the machine learning produces predict fashion. As I said, that would be the sum here. Oh, but we want the probability. So these are the marginal totals. So that's going to be the 197 plus 22 divided by our total number of photos to get 12%. Next, compute the joint probability. That's the probability of two or more variables. The machine learning produces predict fashion, and the truth is fashion. So predict fashion is along here. The truth is fashion is along here. They intersect right here at 197 divided by 1,822 because we wanted the probability is equal to 10.8%. And just a quick note, it is common to substitute a comma for the and joint probability. So instead of writing the machine learning predicts fashion and truth equals fashion, we could do machine learning equals predict fashion, comma, truth equals fashion equals 10.8%. Think of a comma as just separating all the events that we want to consider. This data here is actually a data count, so it counts how many photos. Often we are not given this data, but what we're given are joint probabilities, joint and also marginal probabilities that we get by dividing all of these numbers by 1,822. And this actually should be 100%. It's just rounding error that makes it 99.99%. So I neatened up that joint probability table for truth and machine learning. So here we have the truth equals fashion column, truth equals not column, the machine learning equals predict fashion row, and machine learning predict not row. These totals then for these rows are the marginal probabilities for the machine learning. And then here, these two totals here for the columns are the marginal probability for the actual truth, what the experts say. And then you can read off these probabilities here, these joint probabilities, right? Probability machine predicts not fashion and truth equals fashion. That would be machine learning not and truth equals fashion. That intersection is at 6.1%. So again, the 6.1% is 6.1% of the photos, the variable truth equals fashion, and machine learning equals predict not. And just a warning and a reminder, these are joint probabilities. They are not conditional probabilities. There'll be an example where I will remind you of this so that you don't misuse this table. Now, if we want the marginal probability about the one variable truth, and we want to know if it's equal to fashion, that's that 16.9%. Or we can add through these the machine learning variable. In other words, add the 10.8 and the 6.1 that fall under this column of truth equals fashion, and we'll get the 16.9%. And what this means, if we select 1,000 photos, we expect that 16.9% of the 1,000 photos, that's equal to 169 photos, to be about fashion. And again, it's about fashion because this is truth here. And looking at this percentage for the machine learning predicts fashion, that's 12% or 0.12 of 1,000. If we take 1,000 photos, we expect the machine learning to predict 120 are about fashion. Next, we'll look at the formula for conditional probability. This is the classic way of defining our conditional probability. So the conditional probability of outcome A given condition B is computed probability of A given B. This straight line here means given. Probability of A given B has occurred is equal to the probability of both A and B occurring divided by probability of B occurring. So this is, again, the classic definition. The form that I generally tend to remember because it looks like the multiplication rule is this form here. The probability that both A and B occurs is equal to 1, first the event B occurs, and then 2, now that we know B occurs, A also occurs, but A occurring given B. We can also write that as we know that probability of A occurs, but once A occurs, we need the probability of B given A, because at this point, we know A's occurred, so it has to be B given A. So these are the kind of, this set of formulas, these three are equal. I also like this form because it looks like, and actually it really is, the generalization of the multiplication rule for independent processes. Remember, independent processes means that knowing the outcome of one provides no useful information about the outcome of the other. So this is for independent processes, and you can see the difference, probability of A and B times the probability of A. Now here, if it's an independent process, probability of B given A occurring gives us no additional information about B. So probability of B given A comes down to just probability of B. So again, this conditional probability is just the general form of this multiplication rule. And here's an example of the multiplication rule for independent processes. Suppose we are rolling two dice, one is red, one is white. We want to determine the probability that both will be 1. If the outcome of the red die is 1, it provides no information about the outcome of the white die. So probability of red equals 1 and white equals 1 is probability red equals 1 times probability of white equals 1, which is 1/6 times 1/6, which is 1/36. And writing this in terms of our conditional probability rule, probability of red equals 1 and probability of white equals 1 is equal to the probability of red equals 1 times the probability of white equals 1 given red equals 1. So probability of red equals 1 is 1/6. Probability of white equals 1 given red equals 1. Since they're independent, that's still equal to 1/6. So we have equals 1/36. Now, going back to our attempt to teach a computer how to recognize fashion photography. For part A, determine the probability the algorithm is incorrect. By algorithm, we're talking about machine learning. If it is known the photo is about fashion, this is about truth. So we're using the two variables about truth and about the machine learning. So I'm going to write my formula for conditional probability, but as I said, I like to use this form, the probability, the alternate form, the probability that truth equals fashion and machine learning predicts that it's not. In other words, the photo is about fashion, but we said the algorithm, the machine learning is incorrect, which means it predicts not. So the probability these two items occur is equal to the probability truth is equal to fashion, and the probability machine learning predicts not given truth equals fashion. At this point, we have these joint probabilities, so I can look up truth equals fashion and machine learning equals predict not. Truth equals fashion, machine learning equals predict not. That's 6.1. Probability truth equals fashion, I do have that marginal probability. So I have so far my 0.61 or my 6.1% or 0.061 equals my marginal probability 16.9% or 0.169, and then I'm left with probability machine learning equals predict not given truth equals fashion, and that's exactly what I wanted to know here. So I can solve this algebraically by dividing both sides by 0.169, and I get 36.1%. And this is where I wanted to compare. You want to make sure you realize this is joint probability. It is not count data. Remember when we talked about count data, if we wanted to get the probability that that the machine predicted not, given that it truly was fashion, that would be our 112 over 309. But here, we're not working with count data. Here, we're working with joint probabilities. So you need to use your joint probability formulas. You can't just look in this row and say it's 6.1. That'll give you, obviously, an incorrect answer. Part B now says compute probability machine learning equals predict fashion given truth equals fashion plus probability machine learning equals predict not given truth equals fashion. I'm missing my parentheses again. So I have two conditional probabilities to calculate, and I have my joint probabilities here to use. To calculate this first joint probability, ML equals predict fashion given truth equals fashion, I'm going to use my alternate general formula, the probability that both are true, that truth equals fashion, and ML predicts fashion, and that's equal to probability truth equals fashion times probability machine learning predicts fashion given truth equals fashion. And now I have my joint probability, because I can look that up on the table, truth equals fashion, machine learning predicts fashion, that's 10.8, and truth equals fashion, I can then take my marginal probability, 16.9. So just writing down my numbers first, this joint probability, 10.8% or 0.108. Our truth equals fashion are 16.9 or 0.169 times probability machine learning equals predicted fashion given truth equals fashion. So this is the conditional probability I was asked to calculate, or that I started calculating. Yeah, over here, this part here. I can do the algebra, and I get it's equal to 0.108 divided by 0.169, and I get 63.9%. And now we have predict machine learning equals predict not, given that truth equals fashion. But you know what? That's what we calculated in part A. So we've done B. And then C, we notice if we add these two together, we're going to get 100%. And we want an explanation why. And the reason is, regardless of what the truth is, the machine learning is either going to predict fashion or it's going to predict not. And so these are the only two choices given. Even if it's conditional, it's still the only two choices for the machine learning. So the two choices should add up to 100%, or it should equal to 1. Here we have a new set of data about smallpox inoculation and our results, whether people lived or died. Here is our count data, and here's our joint probabilities and our marginal probabilities and the totals. So just looking at a few of the fields, so smallpox inoculation, yes, so we have 244 people out of 6,224 that are vaccinated. Then for those who are not vaccinated, we have 5,980 out of 6,224 that are not vaccinated. And then here, along the totals, results, we have 5,374 people who lived, 850 who died. And looking at our joint counts then, of the people who had a vaccination, 238 lived, 6 died. Of the people who did not have a vaccination, 5,136 lived, and 844 died. Also, these numbers between how many lived and died, it seems like a lot more was on the no, but that's because so many more people did not take a vaccination, which will also explain now our joint probabilities. So this here is the probability that someone was inoculated and lived. This is some probability someone was not inoculated and lived. Remember, these are joint probabilities. These are not conditional probabilities. The probability that someone was inoculated but died is very small, 0.001, so less than 1%. The probability that someone was not inoculated and died is 0.13, approximately 13%. And these are our marginal probabilities over here on the totals. And these here, again, are joint probabilities, not conditional, but joint probabilities. Now we have some questions. First, write out in formal notation the probability of randomly selecting a person who is not inoculated and died from smallpox, and then find this probability. It's not super clear that they want a conditional probability until you look at the solution, which is what they want. So the probability the person died given they were not inoculated. So we're going to do this from the count data, looking at died, not inoculated. That's 844 out of the total number of people that were not inoculated, 5,980, so that's 14.1%. We are not always given count data, but often are given these joint probabilities. So we're going to now do it from our joint probability table along with our conditional probability formulas. So using this formula here, so the probability result equals died and inoculated equals no, equals probability inoculated equals no, times probability result equals died given inoculated equals no. So probability result equals died and inoculated equals no. That's in the joint. So inoculated equals no, and died is this 0.1356 equals inoculated equals no. That's a marginal probability because it's only about one variable. So that's 0.9608. And that is multiplied by our condition probability result equals died given inoculated equals no. So to solve for this, we're going to divide both sides of the equation by 0.9608, and we get 14.1%, which agrees with the answer we got when we did this from our count data. Part B, result equals died given inoculated equals yes, right? Probability inoculated person died from smallpox. So from our count data, that inoculated is equal to yes. So we're looking at this part of our data. The result is they died. That's 6 out of 244. So from the count data, we get 6 out of 244 equals 2.5%. From our joint probabilities table and our conditional probability formula, we're using this one, probability of A and B, or result equals died and inoculated equals yes, equals probability inoculated equals yes, times the probability results equals died given inoculated equals yes. This we can read off of our joint probabilities, died and inoculated is yes, so inoculated is yes, died, that's 0.001. The probability inoculated equals yes, this is one variable, so we're looking at our marginal distributions. Inoculated equals yes is 0.0392, and that's going to give us our probability result equals died given inoculated equals yes. We divide both sides by 0.0392, and we get probability results equals died given inoculated equals yes is equal to 0.25, which agrees with our count method. So compare our results with Part A. So Part A, the probability of dying if you're not inoculated is 14%. The probability of dying if you are inoculated is only 2.5%. Same data, new questions. The people of Boston self-select whether or not to be inoculated. A, is the study observational or experimental? This is an observational study because the people doing the study collect data and they have no part in how the data arises. B, can we infer any causal connection between these data? And the answer is no, because this is an observational study. C, what are some of the potential confounding variables that might influence whether someone lived or died and also affect whether the person was inoculated? Whether someone lived or died, their general health. Maybe people who are more likely to be in better health will take a vaccination, or it could be the other way around. Maybe it's only the people who are desperate that could take a vaccination, in which case that will bias our sample. Same data, more questions. Suppose we're given only two pieces of information. 96.08% of residents were not inoculated, and 85.88% of those residents who were not inoculated ended up surviving. How could we compute the probability that a resident was not inoculated and lived? So our first piece of information, that 96.08% were not inoculated. Actually, there is one other piece of information we can calculate based on this, and that's, you might take a second to think about it, but I'll tell you what it is. That means that 100 minus 96.08 are the number of people who chose to get inoculated. That's 3.92. Our second piece of information, 88.5% of residents who were not inoculated ended up surviving. So the result was they lived, given that the inoculated was equal to no, 85.88%. And now we want to know about probability that a resident was not inoculated and lived. So our two variables are inoculated and lived. So let's write that conditional probability. So probability result equals lived and inoculated equals no. Inoculated equals no. It's a joint probability. Well, that's equal probability inoculated equals no times the probability result equals lived given inoculated equals no. So let's see what information we have. I guess the idea is that we're not using this table. So let me put a big X because they said we only have two pieces of information. We only have these pieces of information. So the result, they lived and inoculated equals no. So that's what they're asking. So what's the probability equals no? They're not inoculated. We were told that. That's the 96.08. So that's the thing we want to use. And then over here, we have this conditional probability. Result that they lived and inoculated equals no. So those are the two pieces of information we need to calculate this joint probability. We can plug those in and we get 82.5%. One thing I'm going to say is your book has a very subtle difference between when they want to describe a joint probability and when they want to describe a conditional probability. So this here, not inoculated ended up surviving, in your book, that is how they describe the conditional probability. Here, not inoculated and lived, I think it's because it says and lived, that's the joint probability. Next question, I think we're not going to use this table again. It's still about smallpox, but yeah. Use P inoculated equals yes equals 0.0392 and P result equals lived given inoculated equals yes equals 0.9754 to determine the probability a person was both inoculated and lived, our joint probability. So our joint probability is probability inoculated times probability lived and given inoculated. So we're given probability inoculated, we're given the conditional probability, we multiply them together, and we get 3.8%. If 97.54% of inoculated people lived, what proportion of the inoculated people must have died? Well, of the inoculated people, 97.54% lived, that means the 100 minus 97.54% must have died. So 100 minus 97.54, 2.46 must have died. We have already discussed how the conditional probability rule is a generalization of the multiplication rule for independent events. So our last topic for this video is going to be the sum of conditional probabilities. But we can look at this here. So let A1, A2, AK be all the disjoint outcomes for a variable or process. Let's call the process A, has K possible outcomes. Then if B is an event, we have the probability of A1 given B plus probability of A2 given B up to probability of AK given B is equal to 1. In other words, if A occurs, then all the ways that A can occur will add up to equal to 1. And we also have this formula, probability A given B is equal to minus 1 times the probability A does not occur, or A complement given B. This is almost where we end this video, but first we'll summarize what we discussed. We talked about conditional probability. That's when assessing the probability in an event. Knowledge of a different event might change our probability assessment. We talked about marginal and joint probabilities. So marginal probabilities are based on a single variable without regard to other variables, and joint probabilities are probabilities of outcomes for two or more variables together. We talked about the formula for conditional probabilities. So probability of outcome A given condition B is probability of A given B is equal to probability of A and B occurring divided by probability of B. And we have this alternate form that ends up being a generalization of the multiplication rule for independent events. So probability of A and B equals probability of A times probability of A given B. And this formula just comes from here. You just multiply by both sides by probability of B. This can also be switched around, so instead of probability of B first, you get probability of A, then times probability of B given A. Finally, we talked about the sum of conditional probabilities. We let A1, A2, AK be all the possibilities, all the disjoint outcomes for a variable A. Then if B is an event, we have probability of A1 given B plus probability of A2 given B all the way up to probability AK given B is equal to 1. And then from there we also have probability of A given B is equal to 1 minus probability of A complement given B. The tree diagrams and Bayes' theorem we're going to save for our next video. So in the meantime, that's it for this video. Thank you for watching.